The magnetic field of Earth. This styrofoam sphere is going to represent our planet as a northern hemisphere and a southern hemisphere. As the mass moves, notice the north and the south hemispheres move together, and we know that happens and we expect it. At the North Pole, the movement, angular movement, is zero. As you move toward the equator in either hemisphere, it changes till it becomes almost 1,000 miles an hour at the equator. The inside of our planet, the energy of rotation is different than the outside. Notice the northern hemisphere cannot take the energy of rotation of the southern one. I can't put this one directly there and have it be as it was before, nor can I move this one, the south, in place of the north. This represents the energy of rotation, these two arrows inside. The red area within represents the heat energy. The energy of rotation is within our planet is mirror image one of another. When you put this together, the arrows match up. When you take it apart, you see that the rotation is opposite. It is a mirror image one of another. It is like when you stand in front of a large mirror and hold your right hand up. The mirror image holds the left hand up, but in relation to one another, they are the same. And so it is within our planet. Now, through the plane of the equatorial region, there is a strong shearing action because of these two forces of energy moving in opposite directions. It is this opposite moving energy that forms the Coriolis force, where in the northern hemisphere winds move one way, in the southern hemisphere they move the other way, and the same with the waters. It is because the energy of rotation moving from each pole toward the equator is moving in opposite directions. And this is evidenced in the southern region at the equator, in that there's a 25-foot rise in mass in the equatorial region in the southern hemisphere that is not present in the northern one. That's because as the mass is moving in this direction, the energy is moving opposite to it, and it's forcing the matter in that area upward because of the resistance to it. There's a strong shearing action. In the north, energy of rotation and the mass move in the same direction. In the south, the mass moves the same direction as in the north, but the energy of rotation is moving opposite to that of the mass. And what this does, it causes a strong shearing action through our equator, and I'm moving these styrofoam hemispheres, and instead of representing mass, I'm representing the energy. The energy of rotation starts a shearing action. The south is moving opposite to that of north in energy of rotation. This causes a strong shearing action through the plasma area of our planet. A plasma area is where electrons are free to move from individual atoms in the outer shells. It's like a soup, and they're just free to move. When there's a shearing action in the plasma, it causes a great electric field to form. And as the electric field forms through the plane of the equator, magnetic lines form at right angles to it, and that's always true. It does it automatically. When you have a current going through a wire, magnetic lines form at right angles to the direction of the current. Now, what would happen instead of these hemiforces moving opposite to each other? What would happen if actually the energy as well as the mass moved in the same direction? When our planet was created, God created it in a way so that this energy would be expended through magnetic lines. I'd like to illustrate what might happen if there were not magnetic lines within our equator that form. These magnetic lines extending outward from the equator through the polar regions cause the solar wind, which comes from the sun, so that the small atomic particles don't bombard us with their great speeds, causing a lot of damage. This can be illustrated with a fan. If I move these blades when I turn on a current, which I'm not, the electrical lines are expended and the blades begin moving. If I hold the blades, the electrical current that forms magnetic lines doesn't have anywhere to be expended, and pretty soon the motor heats up, it'll smoke, and then it shorts out. It appears that if these hemiforces moving through our equator did not form magnetic lines, there would be a vast heating up through the plane of our equator. It takes a particular kind of mass designed to form a magnetic field. A cone won't work. If we were to use a cone in outer space and spin it, it would not form a magnetic field. It has to have an opposing force. This just has the potential of rotation, kinetic energy. And that's the same with a disk. It wouldn't form a magnetic field no matter how fast it spun in space. A person might say, well, how about a cube? The reason for a cube, or the reason you might consider one, is that it is able to spin. But a cube of itself demonstrates that it does not have the potential to form magnetic lines. The reason for this is its shape. You have to have mass and energy, and then time of rotation to form a magnetic field. In a cube, we have mass, energy, and we would have time, which in the magnetic instance would be that of rotation. But if I were to get rid of the energy, there would be no C2. All we would have would be mass. Like, that's what this would be. It would just be mass. And it could not form a gravitational field. If there were to be a mass like this in outer space, and you were to add an equivalent amount of energy as Earth has, then you would have a C2 value. This is the third part of the physics trilogy. And that cube of mass would then assume the shape of a sphere as we find on Earth. The heat energy would cause the mass to all move toward the point of greatest energy, which would be the point of it. So, in order to form a magnetic field, we have to have the mass, we have to have the energy within, forming a sphere, and then we have to have the movement of it. These three aspects, interestingly, all come together in a single point in forming a magnetic field.